Okay, so welcome to one and all present here. And today we are on week 7, and this is an extra class that we have arranged for you to go through, that is to revisit all the like today we have planned that we'll revisit all the chapters that are being studied in heat transfer. Each and every chapter will solve few problems from there, as it is an extra class to revisit all those topics and all those concepts, so that this will help you out, because next week there is the last class that will be on radiation. So that's why we'll revisit all those topics, cause on your final exam all the topics will be there. Okay, so I think we'll wait for a few more people to join, and then we'll start with today's session. And okay, so after that I'll share the first question of today's session, right? So we'll start with three questions that were left unsolved on the previous day, and then we'll gradually move towards today's question bank. Okay, so let us wait for 3 to 4 minutes for someone to join, like others to join. We already have few people, and after that we'll start with today's session. Okay. Okay, I think it's time we should start with today's session. First, I'll share with previous days question, three questions that are left. Uh, so this is the first question for previous day. So what it said that emissivity or two large parallel plates are maintained at 800 and 300 degrees Celsius. The plates are maintained at these temperatures and its emissivity are given respectively. Find the net radiant heat transfer per square meter for these plates. Net radiant heat transfer, we have to find out, emissivities are given, we know the formula. Find the percentage reduction in heat transfer when a polished aluminium radiation shields of emissivity 0.06 is placed in between them. So when shield is placed, how much reduction in how much percentage reduction in heat transfer will take place, that we need to find out. Also find the temperature of that shield. So first one that we need to find is net radiant heat exchange per square meter, the percentage of reduction in heat loss due to radiation shield, and the temperature of the shield, right? Okay, so we'll wait, like I'll give you 5 minutes to solve this and then we'll proceed with today's solution, the solution of this question. Okay, so take 5 minutes to solve this. It's very easy, like directly formula you have to put. And when shield will be given in between, it's a, like anything that will be given in between the two high emissivity surfaces, then obviously there will be reduction in radiation heat transfer. So that emissivity of the shield is low, so it will reduce the heat transfer. So how much percentage there is reduction in heat transfer, that we need to find. And also we need to find the temperature of the shield. So simply by using the formula that sir have already taught in class, we can find this out. So yeah, this is a lengthy question. So I'll give you 5 minutes first to solve the first part of this question. So first part of the question requires a bit of problem solving. Uh, yeah, first part. Yeah, first part is simple formula. Second part will be required to have problem solving. Basically second and third part. This is combined, right? For the third part, we'll give you the temperature first. So when you will solve the equations, you will get the temperature, and by using the temperature, you can easily find out the radiation when like the radiation heat transfer when shield is present, and then you can simply find out the ratio, and then you convert it to percentage. Yeah, so I'll give you 10 minutes rather to solve the whole question, and then we'll proceed in solving it all together. Okay. Okay, so let us try and solve this question. I hope my writing pad is visible. Okay, so what's happening? First, this 9 of previous class, right? So first of all, there are two walls. One's emissivity is 0.5, another one is also 0.5. Temperature of first surface is 800, of second surface is 300. This is the shield. Its emissivity is 0.06 and temperature we don't. So first of all, let us convert it to, this will be 1073 Kelvin. This will be 573 Kelvin. Right? Now, heat exchange between two large parallel plates without the shield will be Q12 is equal to combined emissivity sigma A T1 to the power 4 minus T2 to the power 4. Combined emissivity is 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. Right? This will be 1 upon 0.3 plus 1 upon 0.5 minus 1. Okay, there is one correction. This is 0.3. I wrote it wrong, sorry. So, this combined emissivity is 0.230. Therefore, for the first part, the net radiant heat exchange per square meter will be 0.230. First, this will be into sigma into area into T1 to the power 4 minus T2 to the power 4. So, this is 0.230 Q12 per unit area into 5.67 into 10 to the power minus 8 into 1073 to the power 4 minus 573 to the power 4. So this will come out to be 15879.9 watt per meter square. Right. Okay. Now, what will happen? Heat exchange. Now, like the heat transfer when shield will be provided between one surface and this is 3, right? So surface 3, this is surface 3. So between one surface and 3 surface will be equal to between 3 surface and 2 surface. Is it okay? So we'll equate both of them at last. So Q13 will be epsilon sigma A T1 to the power 4 minus T2 to the T3 to the power 4. Right? And epsilon will be is equal to T1 epsilon will be is equal to, just one second, epsilon 1 upon epsilon 1 upon epsilon 3 minus 1. This is like epsilon 1 epsilon 2, this all we know. So let us keep it as it is and replace it in Q13. So this will be sigma A T1 to the power 4 minus T3 to the power 4 upon 1 upon epsilon 1 plus 1 upon epsilon 3 minus 1. Now Q1 2 2 3 will be 3 2 will be similar. So this will also be sigma A T3 to the power 4 minus T2 to the power 4 upon 1 upon epsilon 3 plus 1 upon epsilon 2 minus 1. Now this heat will be equal, that means Q13 is equal to Q32. Right? So sigma A T1 to the power T1 to the power 4 minus T2 to the power T3 to the power 4 upon 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1 is equal to sigma A T3 to the power 4 minus T2 to the power 4 upon 1 upon epsilon 3 plus 1 upon epsilon 2 minus 1, or T1 to the power 4 minus T3 to the power 4 upon 1 upon 0.3 plus 1 upon 0.06, cause this cuts off, right? This is same. Minus 1 is equal to T3 to the power 4 minus T2 to the power 4 upon 1 upon 0.06 plus 1 upon 0.5 minus 1. So, T1 is 1073 and T2 is 573. So what this will come up? This will come up to equation T3 to the power 4 is equal to 0.926, 1074 to the power 4 minus 0.926 T3 to the power 4 plus 573 to the power 4. So this will come out to be T3 to the power 4 plus 0.926 T3 to the power 4 is equal to 1.33 into 10 to the power 12. So T3 will come out to be 911.5 Kelvin. So we can find out T1, Q13 or Q32, anything you may like. So 5.63 into 10 to the power minus 8 area into 1073 to the power 4 minus 911.5 to the power 4 upon 1 upon 0.3 plus 1 upon 0.6 minus 1. This will come out to be, this area will go like this. So this will come out to be 1895.76 watt per meter square with shield. So temperature also we know, this is the third part. First part also we found out. Now the second part is required to be found out, that is a percentage. So reduction in heat loss due to radiation is Q without shield minus Q without shield, it will be more, right? So Q with shield upon Q without shield. So this will be equal to 15.87 minus 1.89 upon 15.87 into 100%. This is 88%. Right? This I have just written in kilowatt. This, right? So this is the final answer. Now let us proceed to the next question. You understood this? I don't think there is any problem in understanding this question and this necessary solution. Then we'll move to the second question for the previous class. So what is said, a black body have a total area of 0.045 meter square and is completely enclosed in space bounded by 5 centimeter thick walls. The wall have a surface area of 0.5 meter square and the thermal conductivity is 1.07 watt per meter degree Celsius. If the inner surface of the enveloping wall is maintained at 215 degrees Celsius and the outer wall at 30 degrees Celsius, calculate the temperature of the black body. Neglect the difference between inner and outer surfaces of the enveloping material. There is nothing to understand, like it's just we need to find the black body is enclosed in the huge large space that is bounded by 5 centimeter thick walls, and convection we need to neglect as it's already said, and the material, enveloping material also we need to neglect. Okay, convection we need to consider, conduction we don't need to consider here. So the thermal conductivity, yeah, it's provided. Okay, thermal conductivity is provided, and also the surface area is provided, and the temperature difference is provided. So okay. Here convection we need to neglect. So what said, the enveloping material, okay, if the inner surface of the enveloping material is maintained at 215 degrees Celsius. Okay, so enveloping material, that means convection we need to neglect. So we need to consider here the conduction and also the radiation. So you tell me what is the temperature of the black body. So Q will be Q radiation will be there and one conduction will be there, and that total heat, conduction and radiation, that total heat, like how much it will be. Okay, so under C, if this is a small body and this is the enclosed space, right? So whatever heat, see, there will be some heat that is conducted here, right? That is conducted from here to here. That will be the heat that is conducted from inside to outside through radiation, and conduction we need to be neglected. So this heat that is conducted, that is the heat that you find out from conduction, will be equal to heat that is found out from radiation. So equating that, we can clearly find out the temperature of the black body. It's very easy, right? So I'll give you 2 minutes, rather 5 minutes. Let me give you 5 minutes to solve this, and then we'll proceed with today's solution. Okay, have anyone solved? Or should we wait one more minute? 1 to 2 more minutes. Okay, I think we should wait 2 more minutes and then let someone answer. If not, then we'll proceed with the solution. Okay, it's enough time for this question. I think we should proceed with the solution now because we have a lot of questions left for today. We have not even proceeded for today's question session, right? So, first of all, the heat for radiation by the black body to the enclosing wall is, this is simply will apply the equation for radiation. So this is for the by the black body and this is for the wall. So this is 5.67 in 10 to the power minus 8 into the area is given 0.045 into temperature is TB, black body temperature we don't know, and this is 480 to the power 4, that is 215 plus 273. It's in Kelvin. Now for conduction this will be Ka delta T to the upon delta T upon delta. Delta is the thickness of the wall, that is given as 5 centimeter, that is 0.05 meter. K is given as 1.07 into area is given as 0.5, and this is 215 minus 30. So this will come out as 1979.5 watt, and if we will equate that, what we'll get 5.67 into 10 to the power minus 8 into 0.045 TB to the power 4 minus 480 to the power 4 is equal to 1979.5. Okay. Now, if we will solve this, it will come that TB is equal to 8349.47 to the power 4 into 10 to the power 8. So TB will come out to be 955.9 Kelvin. Right? Now, let us proceed to the next question. So the last question for previous session. So a gray surface has an emissivity at a temperature at a temperature of 550 Kelvin source. If the surface is opaque and emissivity is 0.35, calculate the reflectivity for the black body radiation for 550 Kelvin. Yeah. So for black body, the absorptivity will be 0. So transmittivity will also be 0. So the reflectivity, absorptivity will be 0. The transmittivity will be 0, right, for black body. And also we know that for black body, the absorptivity is equal to emissivity, right? But what if the surface is opaque? For the surface, if the surface is opaque, the transmittivity is 0 anyhow. So the reflectivity, how we can find out? The absorptivity plus the reflectivity will be is equal to 1. So if emissivity is equal to absorptivity, so then from there we can easily clearly find out the reflectivity. Another thing is that a small 25 hole, square hole is made in the thin wall door of the furnace whose inside wall temperature is 920 Kelvin. Emissivity is given of the wall. Calculate the rate of the radiant energy escapes from the furnace through the hole. It's same as the previous question, hole to the room. So we'll directly apply the for black body emission what we need to find out the radiant energy. So we can clearly find out from sigma a t to the power 4, right? So from that formula we can clearly find out if we put all the required values, that is for the black body, right? So if we clearly just find that out by putting all the required values, we will get the radiant energy. That is the energy that is emitted by radiation. So basically we are using the emission power for the black body. For the black body it is sigma to the power 4. So we are just using that for finding out the radiant energy. So that is same only basically. So this is a really easy question, and we have already solved this kind of question earlier. So I'll give you 2 minutes to solve this, and then we'll proceed with the solution. Okay, I think we should proceed with the solution of this question. So, first of all, as I have already said, the alpha plus rho, that is the absorptivity plus reflectivity plus transmittivity, is equal to 1. But for opaque substance or material, transmittivity will be is equal to 0. So what will happen? The absorptivity plus reflectivity is equal to 1, and for black, as it is already said that it is a black body, so sorry, is a gray body. So what will happen? The absorptivity is equal to emissivity. So absorptivity will be is equal to 0.35. Okay. And hence what will happen? The reflectivity will be is equal to 1 minus 0.35, that is 0.65. That is, the surface reflects 65% of the incident energy coming from the source at 550 Kelvin. Now, the small body that is acting as a black body, according to the radiant energy that is emitting from that is E is equal to sigma B A T to the power 4. So this is part A, this is B. So this is 5.67 in 10 to the power minus 8 into area is given as, it is a square substance, 0.25 mm, 0.025 into 0.025 meter into 920 to the power 4. That will give us 25.38 watt. And the data about the emissivity of the inside wall is not needed, obviously. Okay, so I think we should proceed with today's question. That is a mixture of all the sessions that has been held today. So like till now. So it is a combination of the next questions are combination of conduction, radiation, uh, convection inside a pipe or over a flat plate, or rather heat transfer in heat exchangers, and also in a fin, through the fin, right? And I have included all the problems, necessary problems here, so that we can get a reach out of all the, like we can revisit all the necessary, approximately I have tried to cover all of them, cause next week we can end it up with radiation. So so the first question is based on radiation itself. Calculate the heat exchange by radiation between the surfaces of two long cylinders are there, having radius of 120 mm and 60 mm respectively. The axis of the cylinder is parallel to each other, and the inner cylinder is maintained at a temperature of 130 degrees Celsius and emissivity of 0.6. The outer cylinder is maintained at a temperature of 30 degrees Celsius and emissivity of 0.5, and L1 N2 is given as 1. Yeah, because length is 1, like length is similar in both of them. So and L1 L2 is given as 1, so length is also given. So what we need to find out? We need to find out the heat exchange by radiation between both of the surfaces. So it's very easy. We can directly apply the formula based on the emissivities that are given. So yeah, I'll give you 2 minutes to solve this, and then we'll proceed with the solution. Okay, so we should proceed with the solution of this question. So first of all, two cylinders are given, one inside of another. So these are two cylinders, axes are same, axis is same. So these are 30 degrees Celsius T2 and emissivity is 0.5. This temperature is 130, emissivity is 0.6. Now R1 is given, that is radius 1 is given 60 mm, that is 0.060 meter, and R2 is 0.12 meter. We need to find a heat exchange. The heat exchange is equal to epsilon sigma A T1 to the power 4 minus T2 to the power 4. Then epsilon is equal to 1 upon 1 minus epsilon 1 plus A1 upon A2 1 upon epsilon 2 minus 1. So this is 1 upon 0.6 plus pi d1 L1 pi d2 L2 1 upon 0.5 minus 1. So the area as area is pi dm obviously. So this is 0.12 and this is pi, and this will cut off. D1 is 0.12 and D2 is 0.24. Now epsilon came out to be 0.46 epsilon bar. So this Q will be 0.46 into 5.67 into 10 to the power minus 8 into pi D1 into L. D1 is 0.12 into 403 to the power 4 minus 303 to the power 4. So this will come out to be 176.47 watt. Okay. Now, for the second question, let us proceed to the second question now. A furnace radiation is at 2000 degrees Celsius, and we need to consider it as a black body. So we need to calculate the monochromatic radiant flux density at 1 micrometer wavelength. The wavelength at which the emission is maximum, so we'll be using Wien's law. And monochromatic radiation flux, obviously we'll be using Planck's distribution law. And here we'll be using Wien's law, and the corresponding radiant flux we can calculate by this formula that's already given. Total emissive power we can easily calculate as sigma T to the power 4, that is for total emissive power for black body. And the wavelength from 0 to lambda is equal to the emission from lambda to infinity. That is the total fraction of radiation, that is the accumulated fraction of radiation is 0.5, that is F is equal to 0.5. So we can use this graph. So for corresponding F 0.5, F is 0.5, so we can get that approximately sigma t, lambda t is equal to 4100 approximately in this region, right? So we can temperature we know, so we can calculate corresponding lambda. So this is very easy. I'll give you 2 minutes to solve this. I've already explained how to solve, and then we'll proceed with the solution. Okay. So we'll proceed with the solution now. First, as I've already said, we'll be using what? We'll be using the Planck's equation, Planck's law of distribution. So, as this is a black body, we can use that. So, C1 lambda to the power minus 5 exponential C2 lambda t minus 1. So, this is 0.374. The values already was provided on the previous class. So, 10 to the power minus 6 with minus 5 exponential 1.4388 into 10 to the power minus 2 upon 1 in 10 to the power minus 6 into t 2000 minus 1. So this will come out to be 2.81 10 to the power 7 watt per meter square micrometer. Part B is from Wien's displacement law, lambda max t is equal to 2898. So this is lambda max will come out to be 1.49449 into 10 to the power minus 6 meter. So maximum radiant flux, as it's the formula is already given. So maximum radiant flux formula is already given. This is 1.285 into 10 to the power minus 5 to the power 5. So T is 2000. So this will come out to be 4.11 into 10 to the power 11 watt per meter square micrometer. Now, C part, that is total emissive power, will come from Stephen Boltzmann law, that is sigma B T to the power 4. So that is 5.67 into 10 to the power minus 8 into 2000 to the power 4. This will come out to be 907200 watt per meter square. Now, part D is wavelength lambda. As I've already said, f will be equal to 0.5, and we already found out that lambda t is equal to 4100 from the chart. So lambda is equal to 4100 upon 2000 temperature, that is 2.05 micrometer. So we'll proceed to the next question now. For turbulent fluid, so this is basically we are done with radiation for now. Now we got a problem from the convection part. So it is flow inside a pipe. The heat transfer coefficient is obtained from Ritter's-Bolter equation that we already know. If the tube diameter is half and the flow rate is double, the heat transfer coefficient will change by a factor of what? So you just use the Nusselt's number for that, right? So it's very easy. Use the Nusselt's number. You check how the flow rate is dependent on velocity and diameter. So if the flow rate, we know the flow rate is how it is, like if the Nusselt's number is related to the heat transfer coefficient, and heat transfer coefficient in turn, if Nusselt's number is related to Reynolds number in turn is related to the flow rate. So Nusselt's number we can replace in terms of flow rate because velocity is there. So we can directly correlate the heat transfer coefficient to the velocity and also to the diameter. So in this way we can correlate them. So you can just replace that, and then when you find the equation in terms of velocity and diameter, you find the relation. You can directly like apply this conditions that are already given. So I'll give you 2 minutes to solve this, and then we'll proceed with the solution. It's already 11:30. I think you should make it fast. So about this, so there'll be first of all, we'll be correlating Nusselt's number. So Nusselt's number by Dittus-Boelter equation, we know that 0.023, Reynolds number 0.8, and Prandtl number 0.33. So this is hd by k. So hd by is equal to 0.023 dv rho by mu to the power 0.8 and mu cp by k to the power 0.33. So we know that q2 is equal to 2q1 and d2 is equal to d1 by 2. So as q is directly proportional to q, we can see that directly proportional to d square v, because area into velocity, and area is equal to diameter square, right? So and v2 is equal to 8v1 from the, this is from the continuity equation, and v2 is equal to 8 times of v1. It's already given here. Therefore h2 upon h1 will be is equal to v2 to the power 0.8 d2 to the power minus 0.2 v1 to the power 0.8 d1 to the power minus 0.2, right? So this will be is equal to 8v1, v2 is equal to 8v1 is already given 0.8, and d1 d2 is equal to d1 by 2, it's halved, minus 0.2 upon v1 to the power 0.8 d1 to the power minus 0.2. So this is equal to 6.06. Okay, done. This is a gate question. So now we'll proceed with the next question now. A horizontal steam pipe of length 20 meter and 50 mm internal diameter, 60 mm outside diameter, loses 13.5 kilowatt heat to the surrounding at 310 Kelvin. The pipe carries steam at 500 Kelvin. Given the convective heat transfer, and sigma is also given. The emissivity of the bare surface. So here convection and radiation is happening all together. So we'll be using both of them. The values are also given. Both of the here, see here the total heat is given, but it is the addition of both convection and radiation. Okay, so the convection and radiation equations will be applying, that is one Stefan-Boltzmann's equation, and another one is cooling law, latest law of cooling, and both of them will be applying all together, and this will be the total heat that is already provided. Okay, so over there, if we'll be equating both of them, so we can get the emissivity over there, because in Stefan-Boltzmann law we'll be using emissivity, right? So I'll give you 2 minutes to solve this, and then we'll proceed with the solution. Okay, so for this question, there is two parts, right? So first of all, we'll find out the heat transfer through convection. That is the heat transfer coefficient T1 minus T2. And for radiation, this is sigma epsilon T1 to the power 4 minus T2 to the power 4. Now, both of them will add up to give the total heat transfer, that is 13.5 into 10 to the power 3 upon pi 0.0620. This is equal to 1.65 into delta T to the power 0.25 T1 minus T2 plus 6 epsilon T1 to the power 4 minus T2 to the power 4, or 3581 is equal to 1164 plus 3020 epsilon, and epsilon will be is equal to 0.8. Yeah, so let's proceed to the next question now. An aluminium rod, this is based on conduction. An aluminium rod and a copper rod is simple. Both of the rod are of equal length 2 meter and cross sectional area 2 centimeter square, are welded together in series. They are welded together. One is kept at 10 degrees Celsius, the other end is kept at 30 degrees Celsius. Calculate the amount of heat that is taken out per second from the hot end. And thermal conductivity of aluminum copper is given. This is relatively simple, like that this is just parallel resistors. We have to add on the total resistance, and just we have to calculate the total heat transfer. So it's by conduction, so it's like the basic question that we did at first. So yeah, I'll give you just 2 minutes to solve this, and then we'll proceed with the solution. Okay, so let us proceed for this question. The total resistance is equal to the combination of the resistance by the aluminium and the copper. So this is 200 plus this is 390. This is the thermal conductivity. So this is in parallel. So we'll just this will just provide altogether resistance, right? Now the area is 2 centimeter square, that is 20 to the power minus 4 meter square, and temperature difference is 30 minus 10, that is 20 degrees Celsius. I'm not writing all this up. I'll just show you the final one. So this is the formula that we already know. This is 132.2 into 2 into 10 to the power 132.2, 2 into 10 to the power minus 4. This is the area, and this is the temperature difference, and this is diameter. Sorry, the distance between them. Uh, area is 2 centimeters square is given, right? And the length is 2. So this will come out to be 0.2644 watt. Total amount of heat transfer is this. Next one is, this is also relatively easy. Water is pumped through an iron pipe. Its thermal conductivity is given 2 meters long at 1000 kg per minute rate. The inner and outer diameter of the tube are 50 mm and 60 mm respectively. Calculate the rise in water temperature when the outside temperature of the tube is heated. So outside tube is heated to a temperature of 600 degrees Celsius. The initial temperature of the water is 30 degrees Celsius. Specific it is 4.2. Just the rise in water temperature, we need to sorry, tube is heated at 600 degrees Celsius, and the mean temperature, initial temperature is 30 degrees Celsius, and also the specific heat of water is 4.2 kilojoule per kg Kelvin, and the thermal conductivity is given as 67.2 watt per meter square Kelvin. The inner outer diameter of the tube are given, and the length of the tube and the flow rate is also given of the water. So you can clearly calculate the rise in water temperature if you know the flow rate, heat transfer. So the rate of heat transfer, you equate it. So if the rate of heat transfer, like you can equate it to mcp delta T. So SCP is already given. So if you equate it, then you can get the temperature of the water, the later temperature of water from it. Yeah. So do that. I'll give you 2 minutes for this, and then we'll proceed with the solution. I'm going out. I'll be back in 2 minutes. Okay, you solve this one. Okay. So first of all, what we'll do, see, the T2, that is if the inner surface temperature is T2, then this will be is equal to the TW1 plus the 300 sorry 30 degrees Celsius upon 30 degrees Celsius means 303 Kelvin, right? So 303 upon 2. So what is happening basically? First we'll see MCP delta T. So M is given as 1000 into CP is 4.2 into TW2 minus TW2 minus 300. The final temperature minus the initial temperature upon 60. Just kilojoule per second. So this is 70 TW2 minus 303. This is kilojoule per second. Now, also the heat is transferred through pipe, that is given by Q is equal to 2 pi Lk T1 minus T2 upon ln R2 by R1. This is simple by conduction. And T2 we already found out as 2 pi into 2 into L is 2, K is 67.2, and this is 873 Kelvin in Kelvin, T1. That is 600 plus root 73. So there is 873, and T2 we have already shown as 300 plus TW2 upon 2. This is 300. Right. So this upon ln 0.03 upon 0.025. So this will come out to be 4632 721.5 minus TW2 upon 2 kilojoule per second. Now this is equation 1 and MCP delta T1 is equation 2, or vice versa. So we'll just equate both of them. So we'll get 70 TW2 minus 303. I'm just writing it up. You can check this out later. 4.632 721.5 minus TW2 upon 2. So here if we will solve this, TW2 will come out to be 339.5 Kelvin, that is 66.5 degrees Celsius. Therefore, the rise in temperature is equal to TW2 minus TW1, that is 66.5 minus 30. Initially it was 30, that is 36.5 degrees Celsius. Now we'll proceed to the last question for today, and the rest of all we'll solve it on the next day. The boiler wall is made up of two layers, A and B. The thickness and thermal conductivity of A is given as this and this, and for B is given as this and this. Simple. We'll do the parallel. The resistance will be parallel, and it will be added in added up like 1 upon the resistance 1 plus 1 upon resistance 2 is equal to 1 upon total resistance. Just we'll add up like this. And for B is also given, the inner surface of A is maintained at 1000 and the outer surface of B is maintained at 250 degrees Celsius. If the contact thermal resistance is also given per unit area, and it exists at interface. So this will also provide some resistance. So we need to calculate the heat loss per meter square area and the temperature drop at the interface. So it's very easy, like here this is A and this is B. Heat is flowing from here. This is T1, this is T2, and heat is flowing out like this. This will be same. This is LA, this is LB. So this is 240 mm and this is 525 mm. This is T1 is 1000 and T4 is 250 degrees Celsius. This is T4. Okay.
This is T2 and T3 because there will be some resistance, right? And this Ka is 0.2 and this Kb is 0.3. Now the heat flowing per unit area will be is equal to Q. This is the total temperature difference upon the total summation of total resistance. So, okay, I'll give it 2 minutes to solve this rather. I have already told you how to solve this. So we'll wait for, then this will be the last question for today, or we'll take up one more question, and I'll give you 1 or 2 minutes to solve this, and then we'll proceed with the next question, and that will be the last question. Okay, so as I've already said, the total temperature difference between the inner and the outer walls, this will be 1000 and this will be 250, and this whole resistance, summation of resistance, will be 0.24 upon 0.2 for the first one, that is K upon A, plus the contact resistance is given as this 0.05, and the last one is 0.525 upon 0.3. So this means what? This is L upon KA. This is the resistance, right? So A we have taken up. This is Q upon A. So this is L upon K. This is the resistance. So we just have added up because this is in parallel, right? Sorry, series. So this is one resistance. This is the contact resistance, and this is the outer wall resistance. So if we will solve this, this will be 750 upon 3. This is 250 watt per meter square. Again, what we need? We need the temperature drop at the interface. So Q can also be written as T1 minus T2 uh, upon T1 minus T2 upon L by K. L by K, this is L by K, that is 0.24 upon 0.2. Right? This can be written by like this. So this we know, this is 250, and this temperature difference T2 we need to find out, and this also we know. So everything if we'll solve, T2 will come out to be how much? It will be 700 degrees Celsius. And if we will find out, solve for T3 also, T3 also, then T3 also we can write as T3 minus T4 upon 0.525 upon 0.3. So this will be again Q. So if we will solve this, T3 will come out to be 687.5 degrees Celsius. So the temperature drop is 700 minus 687.5 degrees Celsius. Correct? So that means 12.5 degrees Celsius is the temperature drop at the interface. So this is because of what? This is because of this thermal conductivity at the interface. Now, this question is based on the convection. So what is said? Air is flowing on a flat plate at 2.5 meter per second, and the plate length and width is 600 mm by 300 mm, and is maintained at a uniform temperature of 95 degrees Celsius. Calculate the heat loss from the plate if the air flows parallel to the 600 millimeter side, and what the heat loss will be affected if it is parallel to 300 mm side. So in one case, like hk by l na, that sorry, hl by k, that l1 in one case when it is parallel to 600 mm we'll take 600, and when it is 300 we'll take 300. First we'll find the Reynolds number, and based on the Reynolds number we'll see that what equation we'll be using for Nusselt's number. And this is very easy because many on convection, this many problem based on this theory we have solved, right? So I'll give you 2 minutes. This is the last problem for today because it's already 12:17 at night. So we'll be taking 2 minutes to solve this, and then we'll proceed with the solution. Okay. 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 You take 2 minutes and then tell me the answer. So for solving this, what we'll do? Mm, okay. Uh, so we'll first start with the final temperature of T, that is, this is question number 8. So final temperature of T is T bar minus T infinity upon 2. That is, we'll take the average 95 minus 25 upon 2, that is 60 degrees Celsius. Reynolds number is V L upon nu, that is velocity is 2.5, 0.6 for 60 mm side, 18.97 into 10 to the power minus 6. So this will come as 7.91 into 10 to the power minus 4. That is less than 5 into 10 to the power 5. So this is laminar. The flow is laminar. So Nusselt's number is equal to 0.332, Reynolds number 0.5, Prandtl number 0.33. So 0.332 into Reynolds number is 7.91 into 10 to the power minus 4 to the power 0.5. Prandtl number is 0.696 to the power, Prandtl number is 0.696 to the power 0.33. So this will come out to be 82.76. Now, uh, what will happen? This is the local Nusselt number, right? So for laminar flow, we know that the average Nusselt number is twice of the local Nusselt number. So this will come out to be 165.52. So the average Nusselt number is equal to h bar L by K. So this is 7 point, like it's so h bar will be 165.52 into 0.02896 upon 0.6. So this is 7.989 watt per meter square Kelvin. Kelvin to Kelvin. Okay. Now, so we have to find Q. Q is H bar A delta T. That is H bar, that is 7.989 into area is how much? Area is 0.6 into 0.3, width into length. And this is 95 minus 25. So this will come out to be 100.66 volt. Now, for the second case, what we will do, we will take L as 0.3 and width as 0.6. So this is nothing but all the calculation will change. Reynolds number will come out to be, I'll just write the values, you can check it out later. So this will come out to be this, and this is less than 5 into 10 to the power 5. That is, the flow is laminar. Now Nusselt's number will come out to be 0.332 into Reynolds number 0.5, Prandtl number 0.33. So 0.332, Reynolds number is 3.95 into 10 to the power 4 whole to the power 0.5 into Prandtl number is 0.696 to the power 0.33. So this will come out to be 58.48, and Nusselt's number average will be twice of this. So this is 116.96. And if you'll find H bar, that will come out to be 11.29. So Q will come out to be H bar A into delta T. So H bar is 11.29 into area is 0.6 into zero point 0.3, and delta T is 95 minus 25. Again, the temperature difference will be same only. So this is 142.25 watt. So what will be the heat loss? The heat loss is equal to Q2 minus Q1 upon Q1 into 100%. So this is 142.25 minus 100.66 upon 100.66 into 100%. So that is equal to 41.32%.
Okay, so with this, I'll end today's class, and let me show you the other problems. You can take like this video will be available in YouTube, right? So you can pause it and you can check out the next question. So this is question number 9, this is 10, this is 11, this is 12, and this is 13. And this is the last question, 14. So these questions are left for today. Actually, there is a lot of questions that I have marked for today, but because of the less time and previous day's question, we were not able to solve all this. So these questions I'll take up on the next session. That will be the last session for this course, problem solving session. I hope all of you will be present there. And if anyone will have any problem, do discuss on the last session. And this video, for those who have not joined, will be available on YouTube, so you can check out the problems and the time allotted for that problem. Use that time only. That time is more than sufficient for solving that problem. And then you can check out the solution that I have already done in the class, and the questions that are left, you can take the like photo image from the video, and then just one second. Yeah, and then you can solve it back at your home, and on the last session you can discuss that problem with me, so that I can solve your doubts. Okay, so I'll meet you up next week, and the PPT I'll upload in the drive, and I hope the drive link is also shared with you. So yeah, let's end it here. I'll meet you guys next week. Bye bye.